Welcome to this explainer. I am absolutely thrilled we're taking this journey together today because we're doing something really cool. We are taking some incredibly advanced, heavy-duty control mathematics literally right out of the textbook, and we're breathing life into it by putting it into physical hardware. If you've ever found yourself wondering how abstract math actually controls the complex machines all around us, well, you are in the exact right place. Okay, let's dive right into this. I want you to picture the classic, highly unstable problem of balancing a broomstick on the palm of your hand. You know the drill, you have to constantly dart your hand back and forth just to keep it from toppling over. Well, in the engineering world, this is known as the inverted pendulum problem. It's a notoriously difficult challenge because the system is what we call under-actuated and it's highly nonlinear. Now, if you try to slap a traditional PID controller on this, it completely fails. No way it works. It just cannot handle that extreme level of instability. So we're going to need a much smarter approach. So here is our roadmap for today. Think of it as our theory to reality bridge. First up, the classic control problem. Second, building the actual hardware. Third, the swing-up phase. Fourth, the balancing act. And finally, number 5, simulation meets reality. Section 1, the classic control problem. Mastering highly nonlinear instability. Let's frame exactly what we're up against here. We are basically facing a dual objective problem. First things first, we have to swing a pendulum from a completely stable, dead-stop downward position all the way up to an upright position. Then, objective 2, keep it perfectly balanced there. And the catch? We can only use the horizontal movements of the cart it's attached to. But before we can even think about controlling this thing, we have to actually understand it. To map out the forces we're dealing with, we use Euler-Lagrange equations. This mathematically models the system's total kinetic and potential energy, giving us a precise map of its nonlinear behavior so we know exactly what we're dealing with. Section 2, building the hardware, from scrap to a scientific instrument. Let's ground these abstract math concepts into a real physical setup. What's really wild about the hardware here is the track the cart actually moves on. We aren't using some $1,000 piece of lab equipment. That linear guide was actually salvaged from a defective inkjet printer. Seriously. Pair that scrap with an Arduino Mega 2560 acting as the brain, a high-power Cytron EC motor driver, and some high-resolution 600 pulse per revolution encoders that give us incredibly precise linear and angular position feedback, and you've got a beautiful example of resourceful engineering. Section 3, the swing-up phase, injecting energy to overcome gravity. Now we get to introduce the very first brain of our control logic. This brilliantly illustrates what I like to call the two-brain analogy. It's really a stark contrast. We simply can't use one single controller for the whole process. The swing-up controller is our brute force energy injector. It uses an energy-based approach with partial feedback linearization to make these large, sweeping, dynamic movements. It's literally pumping energy into the system. But the balance phase? Completely different brain. That one uses a linear quadratic regulator for precise, microscopic, acrobatic corrections. Let's look a little closer at that first brain. So the entire goal of the swing-up controller is to reach what's called a homoclinic orbit. That is the exact trajectory where the pendulum swings up and hits the completely upright, highly unstable fixed point with exactly 0 velocity. The controller's job is to swing the cart back and forth, carefully regulating the mechanical energy of the system to place the pendulum perfectly onto this specific path. It basically arrives at the top perfectly at rest, just begging to be balanced. To hit that perfect orbit, we have to completely control the total amount of energy in the system. In practice, we achieve this using something called collocated partial feedback linearization. Now, I know that sounds pretty intimidating, but actually, scratch that. It just means we're mathematically converting all those complex force equations we looked at earlier into one simple maximum acceleration command that our Cytron DC motor can actually deliver. We are telling the motor exactly how hard to push to shape the energy of the pendulum. Section 4, the balancing act. Enter the linear quadratic regulator. Once that pendulum swings up and enters a specific threshold, say it gets within 15 degrees of vertical, our system physically switches over to the second brain. But wait, before we just blindly apply our L2R balance controller, we have to prove mathematically that balancing is even possible in the first place. We do this by checking the controllability matrix. It's essentially a mathematical reality check in MATLAB to confirm, yes, the motor actually has the physical authority to move this pendulum to a stable state before it falls over. We also double-check the stability by looking at the eigenvalues of the system state matrix. Okay, so once we know it's controllable, we apply the linear quadratic regulator. The crucial takeaway here is this. Instead of getting totally bogged down in massive, complex matrices, just understand that the LQR is simply an optimization machine. It uses the algebraic Riccati equation to minimize a cost function. It's constantly calculating the absolute best, most optimal path to keep that pendulum upright, while minimizing how wildly the cart has to jerk around to do it. It just perfectly balances control effort with accuracy. So what do the results of this two-brain system actually look like? 3 to 5. In testing, the swing-up controller successfully elevated the free-hanging pendulum all the way to an upright position and cleanly handed it off to the balance controller in just 3 to 5 seconds. I mean, that is incredibly fast and efficient. Section 5, Simulation Meets Reality, deploying MATLAB logic to the Arduino Mega. This is, for sure, the most satisfying part of the engineering design process, where we finally put all our code to the test. We are finally crossing the bridge from the computer screen directly into the physical world. And the pipeline here is beautifully streamlined. We load the parameters into MATLAB, open up our Simulink model, which contains both our swing-up and LQR controllers, and deploy it straight to the Arduino Mega using the Arduino support package. The Arduino then completely runs the show. It takes in real-time continuous feedback from those 600 PPR encoders via serial communication, crunches the math, and fires the motor driver. The physical experiment was just an incredible success. The pendulum swings up, and the LQR controller takes over with very minimal overshoot. And beautifully, the actual hardware response closely matched the simulation data we calculated beforehand. The only minor discrepancies came from things you just kind of can't perfectly simulate, Things like real-world motor friction and a tiny bit of electrical noise in the encoders. But the controller was totally robust enough to handle it, keeping power consumption well within acceptable limits. So I want to leave you with this thought. We took an incredibly unstable system, modeled the raw physics, built a rig out of an old defective inkjet printer, and balanced it flawlessly using an Arduino. If we can do all of that, what other seemingly impossible real-world physics problems can you solve with model-based control? Think about the massive aerospace and robotics applications out there just waiting for these Simulink and LQR concepts. The math is powerful and the tools are literally right at your fingertips. Thank you so much for joining me on this explainer, and keep exploring.